Hey guys, it's Sid the Magician, and today I'll be talking about limits, finding limits graphically and numerically, and undefined limits. So I'll do some examples here. So first we're going to do the limit of f of x. So for this function it will be x cubed minus 1 over x minus 1 as x approaches, let's do 1. Okay? So the value, if you plug in 1 here, you're going to get 0 over 0, so you'll get undefined. But we're trying to find the limit, not the actual value of it. So I'll draw the graph. The graph looks somewhat like this. Now, the basic thing you need to remember for a limit is that we have to find what the limit approaches from the left side and what the limit approaches from the right side. So at x equals 1, it's this value right here. Now, the left side, what does it approach? And what y value does it approach? And from the right side, what y value the function approaches. So I'll draw a quick table here for x and for f of x. And let's do values that are close to 1, but not 1, from the left and right side. So I was thinking we do 0.99 actually. And then we'll do 1, and then we'll do 1.001, okay? Now, if you plug those in, which I will plug them in right now, 0.999 cubed minus 1 over 0.999 minus 1, we're going to get 2.997. Now, this is, we don't know. If you plug it in, you'll get 0 over 0, but that's not what we're looking for here. And later on, I will teach you guys how to find a limit with this function. There's some factoring involved with this function. But for now, I'm just talking about tables and graphs, how to find limits using those ways. So I'll just type this in, 1.001 cubed minus 1 over 1.001 minus 1. Now we get 3.003. Do you see that? Now, if the left side approaches 3 and the right side approaches 3, we can confidently say that the limit of x cubed minus 1 over x minus 1 as x approaches 1 is 3. So the limit is 3 because the limit from the left side and the limit from the right side are the same. Now let's do another example. Let's do x over square root of x plus 1 minus 1 as x approaches 0. So what does this limit equal? So we'll have a graph here, which I think, I've graphed it right here. It looks like this. So there's a hole here actually, small hole, because when you plug in 0 here, you're going to get undefined as well. But there's no factoring out this time, so there really is no value here. It's undefined. But we don't care if the value is undefined or defined. We just want to know what it approaches. So for this one, all we have to do is the same thing. If it approaches the left or the right side. So from the left side, we just make a table of f, and I'll just write f of x. I don't really want to write all that down. And then it's as x approaches 0. So we'll do negative 0.001, 0, which we know it's undefined, but we're trying to find the limit, and then 0.001. Now I've already plugged these in. You get 1.995 and 2.000499. Now the left side approaches 2, the right side approaches 2. We know that the limit is 2. We'll do one more example where the limit does exist. So we'll do the limit of, I'm thinking we should do f of x, a piecewise function. So f of x equals 1 or 0, depending where x doesn't equal 2 and x equals 2. So basically, f of x equals 1, all values except 2. And then it equals 0 when x is 2. So if I draw a graph, this is 1, this is 0. Every value except 2. So we have 1 here. And then we draw a straight line. Let's say this is value of 2. There's a hole here, but the value is actually here. So it's still continuous. and then we'll talk about continuity later. And then we have a video. The line continuing over here. Now, same thing. Left and right side. Left approaches 1 because every value is 1 except 2. Right approaches 1. Therefore, we can say the limit of f of x as x approaches 2 is in fact 1. Now, let's do examples where the limit does not exist. There are 3 criteria. So, limit does not exist. Okay? For 1, left and right side. And I'm going to abbreviate all these 3 things. Left and right sides differ. So I'll write limit above these. So limit from the left and limit on the right have to agree. Number 2, f of x increases or decreases without bound, meaning going to infinity. Which means there's one more. Oscillating behavior. So I'll do an example of each of them. So for the first one, we have the limit as x approaches 0 of absolute value of x over x. And then we have the function. It's going to look somewhat like there's a whole it's kind of like a step function, if you know what that is. Basically, it takes, I'll show you. If you plug in -1 in here, you're going to get 1 over -1. So we get -1. So this value always -1. It's kind of like the least integer. So if your value is 1, if you plug in 1, you're going to get 1 over 1, so you're going to get 1, right? Now, let's say you plug in 1.5. You're going to get 1.5 over 1.5, which is 1. You're just going to keep getting 1. Now, what's the absolute value of 2? 2 over 2. It's 1. So it's just -1 or 1, basically. It's kind of like the example above that we did. But at 0, it's something different. Because obviously you have 0 over 0, so it's undefined. Now, we don't care. We just need to look left side and right side behavior. Okay? So from the left side, approaches -1, if you see here. From the right side, the function approaches 1. But these do not equal. So here, I'll denote it as limit of f of x. I'll write this as f of x. As x approaches 0, from the left, negative sign denotes from the left side, does not equal the limit of f of x as x approaches 0 from the right, which is a positive. So that's why we'll have to say this does not exist. So DNE, short for does not exist. Now let's do another type in which f of x increases or decreases, so unbounded behavior, without bound. So limit as x approaches 0 of 1 over x squared. So for this one, let's say we have a function. This actually goes, this is what the graph looks like for this one. And we'll say it goes to infinity. So infinity, it does not stop. That's why it's unbounded. Now, for this one, it's pretty simple. We need an actual value to say here. The left side goes to infinity. The right side goes to infinity. So actually, technically, you can say this equals infinity. You can say the limit as 1 over x squared from x approaches 0 is infinity. And you can also say the limit, since infinity is not really a number, it's a concept, you can say limit as limit of 1 over x squared as x approaches 0 does not exist. So you can say both of these work. You'll have to ask your teacher about the specifics if you're allowed to say either, but both of these work for that one. Next, we'll talk about oscillating behavior. That's the last thing for this topic. The limit as x approaches 0 of sine 1 over x. So limit of sine over 1x, sine 1 over x as x approaches 0. For this one, it's pretty simple as well. For the graph, I kind of want to type in the graph here because it's going to be hard to graph this one. So I'll do sine 1 over x. For this one, it'll be hard to see. But you see that oscillating means back and forth. Do you see that back and forth wave behavior in the middle close to 0? So if I'll zoom in, so hopefully I'll see it. Yeah, you'll see it here. You see here, it's like moving back and forth, right? So the function, if I try to draw it, it's going to be oscillating like crazy in the middle and then continue. Now for this one, since basically if you were to draw a table for this one, so we'll have 2 over pi, 2 over 3 pi, and we'll do 2 over 5 pi as well for x, and then f of x, you're actually going to get 1, then -1, then 1, and so on. So it's oscillating between what values? You guessed it, 1 and -1. Meaning, this limit does not exist, because some could say 1, and some could say -1. And you don't just take an average and say 0. That's incorrect. So the limit of sine of 1 over x as x approaches 0 does not exist due to oscillating behavior. Thank you for watching this video. More to come later.